Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar lecture theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the SwayamPrabha course on maritime structures under fire, blast and explosion, jointly organized by me and Professor Gaurav at IIT Gandhinagar, Department of Maritime Engineering. We have learned in the previous lectures about how to compute the blast loads, how to compute the consequences arising from explosions, etc. Welcome to lecture 25 where we are going to talk about some design guidelines for blast loads. The moment I say blast load, then we must know how to estimate the blast load, which we have learned in the previous set of sequel lectures. We have also learned how to estimate the damage consequence caused by the blast load. We will pay more attention to this for the time being and then we will extend this for design guidelines under blast. So therefore friends, to assess the consequences of blast, The primary requirement is to compute something called blast overpressure. We have already learnt it, but I am just trying to re-emphasize on this for clear understanding further once again. This overpressure along with the duration of impulse defines the severity of explosion. Okay, that is how we do it. So, what we first do will be the steps involved in doing this consequence. So, in step number 1, we compute something called the flammable inventory. So, if you recollect, we said the flammable inventory is always computed in terms of TNT equivalence, whereas TNT is a designated explosive which understands and whose consequences are very well established in the literature. Therefore, whatever inflammable material you have of combustion material you have on the stock on maritime structural deck or on any processing industry, we first compute the TNT equivalence of that. We have a standard equation which we have already given you in the previous sequel lectures, but we will once again insist that we must know how to compute the TNT equivalence. Once we do this, then for the TNT equivalence or the flammable inventory, we compute something called scaled distance expressed as ZE. So, ZE actually depends on the actual distance of the point of interest from the source. Okay? ZE actually depends on the point of interest where you want to compute the consequence of blast, point of interest from depends on the distance of point of interest from the source of blast. Okay. So, we have a standard equation which we already discussed. ZE can be given by R 1 by 3 of m, where R is the actual distance from the explosion to the point of interest, and m is the mass of explosive, which is generally done in kg, which usually and preferably expressed as TNT equivalence. So, once I know the mass of explosive and the actual distance, I can compute the scale distance. Once I have the scale distance, then we can assume a standard scenario of blast and compute the damage. Okay. So, to compute this damage, we need to compute further something called scaled overpressure, because the damage is does not depend on ZE, but depends on scaled overpressure. The scaled overpressure P naught can be computed using this equation. Let us say P naught scaled overpressure is atmospheric pressure of 16 1 plus Z E by 4.5 square divided by square root of 1 plus ZE by 0.048 of square into 1 plus ZE by 0.32 square into 1 plus ZE by 1.35. Oh, these are all squares for these. One moment, let me correct this equation. So, square of these times square of these times square of these times and the whole root. Okay. So, now in this equation P naught is the peak incident overpressure, which we need to compute, because based on this P naught I can always compute the damage consequence, and PA is the ambient pressure, and of course ZD is the scaled distance in meters. In fact, the unit will be not meter, it is actually depending on the fuel load. So, m by so many kg of 1 by 3. If you look at the unit of ZD, meter by kg, right. So, that is what we are looking at. So, once I know P naught, using the standard blast curve results, I can always compute the damage consequence. Okay. So, now if you also want to find the absolute overpressure acting on any surface, I can always compute that as Ps is this P naught with multiplied by P. So, P naught will accelerate, will enhance the atmospheric pressure to give me the absolute overpressure on any surface. Okay. So, the damage consequence interpretation is qualitative. So, if we have computed the overpressure for P A computed, sorry, P0 computed, for P0 computed, then if this value is 15, 20 to 40 kilopascal, then we can say there will be a facade damage to the building. If this value is from 50 to 100 kilopascal, then we can say there will be a minor structural damage. There can be some wall cracking. If this exceeds to 300 kilopascal, then there will be a partial collapse of the structure and there will be equipment damage. If this exceeds further to 300 kilopascal, then I can say there is a severe structural failure and life threatening damage will happen. Okay. So, these are some qualitative indices. To know this, we have to compute P naught, and P naught is available in this equation if you know atmospheric, if you know scaled distance. Okay. So, qualitatively you can compute this, and this curve will help you to compute P naught other than from the equation. Let us say if I know the ZE value, I can find directly the scaled overpressure, which we already have it here in this equation. Okay. We compute P naught, then we compute Ps. I can always directly do this from this equation. If I know the scale distance, I can directly compute the scaled overpressure. If I have the scaled overpressure, if you want to find P naught, I can divide this PA, I can get P0. If you know P0, by comparing this, I can always find what damage the structure would encounter. Okay? So, that is the table available in the literature. If you know the peak overpressure, you can quantify the damage arising from explosion for various values. I have given you a large picture, even for small values as well. You can find out a very clear definition available in the literature for quantifiable damage. That is how the explosion damage are actually quantified. Let us quickly do a problem to understand this. Though we did this earlier in a different picture, let us do it again. Let us say I have a blast charge of about 50 kg RDX, okay, identified in some port office in building. The office building is of size this. So, 10 meter by 8 meter is the plan size and 30 meter is the height. So, what we wanted to find out is determine the standoff distances. If you remember the previous sequel lectures, we have given you equations how to compute the standoff distances on the front face of the building, on the side face of the building and on the top of the building if you have a blast source available in front of the building. So, now we wanted to find out the same here, then we will extend this to also find out what would be the damage consequence of the scaled distance. So, it is very simple. The standoff distance for different locations of the building, front, side and top, these equations are already available in the previous set of literatures. So, R in this case is the source distance, H in this case and B are the breadth and height of the building respectively. So, I have taken 10 meter by 8 meter is the plan size, height is 30 meter. So, 30 substituted. So, the front face standoff distance is 101 meter, the side face standoff distance about 104 meters and the top side standoff face distance about 108 meters. So, for every one of these standoff distance, I can always compute the scaled distance. We just now saw the equation. So, before that, let us compute what is the equivalent TNT mass of this 50 kg RDX. So, this can be expressed as so much. So, the TNT equivalence is about 4184 joules per gram. Once we did this, then I compute the TNT equivalence of so much, then the scale distance is computed from the equation. I get the scale distances for different locations, front of the building, side of the building and top of the building. Let us say this refers to 101.2, possibly refers to the front side, 104 refers to side. So, this refers to front, 104 refers to side face of the building, this is front face of the building and this is top face of the building. For example, I have a building which is 30 meter high, okay, and this is the ground. There is a blast source available here on the ground, which is about 50 kg RDX, okay, or an explosive or any flammable material, right. So, if I say this is my front face of the building, this is my side face of the building, this is my top face of the building, I call this as 10 meter, 8 meter and this is 30 meter. I can also find the effect of this blast on this face and on this face and on this face. That is what we have done for this equation. So, front face has scale distance so much and so on. Once I have the scale distance, friends, I can always find peak overpressure from this curve. From this curve, I can always find, if you know the scale distance, I can always find the scaled overpressure. If you know the scaled overpressure from this equation, I can always find the peak overpressure. If I know the peak overpressure, I can always find the damage. So, if I place any flammable combustible material in front of the building, what would be the effect of that on fronts and top faces are now estimated. So, explosion damage consequence can be assessed like this. Let us take one more example. Let us say a cylindrical vessel of volume 50 cubic meter contains liquid propane. It is a very common example what we have in inventories of offshore platforms which explore or process oil. It is kept at a room temperature of 25 degrees Celsius. Now, it undergoes levy because it is under compression and it is under high pressure. Therefore, a fissure or a crack can cause a levy due to fire engulfing the whole containment, and that leaks happen through a safety valve. So, at the time of explosion the temperature was 50 degrees, okay, and the filling degree was 25 degrees. Estimate the scaled overpressure at a distance of 125 meters from the source of this levy. So, we have already know the 50 degree Celsius converted to kelvins, and we know the filling degree 0.25 expressed as percentage, right. So, 25 degrees is about 0.25. So, volume of the vessel is known, liquid density is given because it is liquid propane, propane density at 50 degree is this much, liquid volume is now known, and mass of propane is computed based upon its calorific value, and burning efficiency we usually assume for any value from 10 to 70%. So, let us say 10% burning efficiency, we compute the energy release in megajoules. So, with the energy release in megajoules is known, depending upon the calorific value of TNT, you can always find the TNT equivalence. Once the TNT equivalence is known in terms of mass, I substitute that here and compute this distance. Okay. So, once the scale overpressure is understood, scale distance is known, you can compute the scale overpressure from the figure and compute the pressure, and for the pressure I can always compute the consequence. Okay. Friends, very simple illustration. If I say that the pressure is expressed in bar, okay, 1 bar is actually 100 kilopascal, though bar is not a metric unit, but expressed generally in bar. Okay, it is not a part of the system international. So, it is 100 kilopascal is 1 bar. So, why do we express pressure in bar? Very simple. It is because that 1 bar is slightly or more or less equal to the average atmospheric pressure on earth at sea level. So, since in maritime structures we talk about the sea surface elevations and always ocean wave hydrodynamic loadings, we would like to express them in pressure because that is the equivalent bar or 1 bar is that atmospheric pressure applied on the earth at the free sea surface level, which is approximately 1.013 bar. So, that is why we express the pressure in terms of bar, and 1 bar is about 100 kilopascal. So, if you know the value of pressure, you can always compute them in terms of bars, and let us say how do we relate this to this. Having said this, so we have now understood how the scaled overpressure helps us to compute the consequences of this. Okay. Having said this, let us go forward and learn in case of reinforced concrete buildings, what kind of recommendations we propose for blast resistant design. 1. The reinforcement must be anchored beyond the plastic range or the plastic hinge zone. What does it mean? If I have a beam which is fixed, which is also centrally loaded, you know, these are the 3 potential points where plastic hinge can happen. Plastic hinge is not a point, it is a section. Therefore, the plastic in the center can be effectively for a specific length, let us say L1. Plastic hinge at the support can also be for a specific length L2. I will take it symmetric in both cases. Okay. So, the anchorage of reinforcement should be beyond these ranges actually, right. I should extend the bar, if it is fixed, then I should extend the bar to the support and have an anchorage for the reinforcement. This is the support, let us say, and then anchorage. So, the bar should extend beyond the anchorage point of the plastic hinge zone. Okay, that is very important. The second one could be closed syrups are necessary. Are required. You know, stirrups are generally provided for shear check, so are required to prevent shear failure. And this also helps to enhance ductility. The third could be any sudden change in cross section along the length of the beam, or the column, and re-entrant corners should be avoided. These are general design guidelines for blast resistance. Why are we saying they should be avoided? Because these are the points where the stress is concentrated. Okay, so we should avoid this, right? So these are the three conditions what we must fulfill, and the fourth one is much more important, which is quite logical. The fourth one is provide continuous load path in the system. Do not break the load path. Okay. So this will help maintain integrity of the structure even after partial failure. That is the advantage if you have a continuous load path. Okay. So blast resistant detailing is not only about increasing strength, is not only to increase the strength, but the most importantly, it ensures good deformability of the structure. So, no sudden failure is initiated. Okay, that is the requirement what we say in the design. Therefore, design should be based on the following. 1. The member function, member location, then anticipated blast load, and of course, we must ensure that a continuous load path. Having said this, so we have already seen that we can use equivalent single degree freedom system approach. So, we have seen that equivalent single degree freedom system approach is one of the methods to analyze structure under blast. Okay? We have already seen that. So, the approach therefore confirms that the structure has safety, resilience, and structural continuity even under extreme load conditions. It ensures that. Now, when you have blast loads occurring on structures, structures may also end up in having progressive collapse. Though the idea is not to have a progressive collapse, but if the progressive collapse is initiated, then the structure should resist resistance against progressive collapse is desired. So, what does it mean? When a small part of the structure, I should say, or a component, or I should say, or a member fails, it should not lead to chain of failures. Okay? We must ensure that. So, then one can ask me, what are the practical situations where this can happen? The practical situations where such progressive collapse can happen are loss of a critical beam. Critical beam is usually either heavily loaded or large span. Both ways they are critical. Secondly, there can be a loss of a column member would have failed, or there can be a loss at any intersection, that is connection, joint can also fail. So, when such elements fail, there is a high probability that it may lead to a progressive collapse. So, one should check that they do not occur by design. Then one can ask me a question, what are the types of progressive collapse? What are the types of progressive collapse? So, there are various types in the literature, what we call as a pancake collapse, where the vertical, where the floors fails vertically due to failure of columns. Second could be zipper collapse. Zipper collapse is a sequential failure of connected or interconnected components. We should say interconnected components. For example, secondary beam failed because it is pulled by the primary beam. Okay? So, it is a zipper failure. 3. Instability collapse. Instability collapse is due to buckling of column members, due to LTB of beam members. You know what is LTB? Lateral torsional buckling of beam members. They all will initiate instability collapse. Something called domino collapse. The sequential failure of adjacent columns. like it falls as a pack of cards. Okay. Once we understood the failure collapse modes and patterns, then what should be of descent strategies? Or blast loads, the design guidelines. We must always ensure that the structure has got or possess alternate load path. Even under sudden removal of a column member, a supporting element I should say, okay, supporting member, the structure has ability to shift its load path to the adjacent vertical support system. Okay. This idea was suggested by carrying out a nonlinear modeling design or modeling and design uniform UFC code in 2016 onwards. The second could be what we call as a tie force method. That is another design strategy. This method ensures that all components of the structure are tied together, okay, or tied together with sufficient tensile capacity. I mean that you must realize. See, we know the strut and tie model of a structure. Struts are compression members, they take axial compression. Tie are tensile members which take axial tension. The structure can be always modeled as an equivalent strut and tie modeling. So, the tie force method will help us to understand and realize that all members and all components in a structural system should be tied together. So, how do you achieve this? One can ensure that there are vertical ties which connect floors and roofs to the column. So, we call this as a vertical tie, which generally we do. Second could be horizontal ties, where the beams and floors are connected at the same level or the same floor level or connect across spans. The third one could be peripheral ties, which holds the external members together. This allows effective redistribution of load, or let us say the moment, and helps us to identify alternate load path. Okay. The third method could be enhanced local resistance. So, instead of relying on the redundancy, structural redundancy, one can strengthen the key elements of the structure locally. For example, one can use stronger columns. You can also reinforce the joints additional. Okay. ACE advises this kind of system. The fourth could be improving redundancy and ductility. So, structures should be designed or should be planned, I should say, should be planned with more load paths. And ductile detailing should be more resilient. Redundancy ensures that failure one part does not interrupt with the function of the whole system. So, redundancy helps or redundancy checks that one part does not influence the other's failure. And ductility ensures that even at failure, the structure gives enough warning. Okay. So, what are the specific recommendations what we can do for preventing progressive collapse? One, reinforcement continuity across joints is essential. To avoid sudden change in cross section. Or member layout. 3, tie reinforcement should be provided continuously. What we call, you must have seen in buildings, we use something called tie beam, which will connect all the external members as one go. One should use closed stirrups to enhance the shear resistance. One should prevent weak joints. The joint should be stronger. Okay. So, therefore, friends, let us look into the design considerations or the design recommendations. What are the factors which are important in blast resistant design? One is the strength and redundancy. One should ensure that the structure should have high strength members and materials and the structure should have alternate load paths. Okay. High strength material should have alternate load path. The second is enough ductility. The system should provide good ductility and it should avoid brittle failure. Three, the system should have enough anchorage of ductile detailing. The rebars should extend beyond the plastic hinge ranges. Okay. Strong connections. Okay. So, we should use full length weld, high grade bolts in case of steel structures, and we can also recommend mechanical connectors as splicings, extra splicings in concrete systems or even in steel structures. In reinforced concrete, one should use lap splices, one should use mechanical couplers, which are generally located away from the plastic hinge zones. In steel structures, one should use welded connections over bolted connections. Prefer welded ones than bolted ones. In beam column connections, they should be designed for combined effect of bending, shear and axial force. One can also use something called protective systems and barriers. Or blast resistant design. Protective systems are those elements which are used to delay, these are those elements which used to delay the transmission of blast loads. There are several types of systems. Let us say what are the types of protective systems. One, I can have blast walls and standoff barriers in the structure. Blast walls are designed to reflect, absorb or redirect blast waves. So, blast walls will absorb or redirect the blast waves. The materials for blast walls could be materials of construction, could be reinforced concrete, can be even simple masonry with steel backing, or it can be even sandwich plates or sandwich panels. You must have seen in many strategic structures, people use sandwich panels as blast protection devices. They should be anchored to the foundation. to resist overturning failure, and they should be placed at proper height and spacing all along the circumference of the structure. Okay. The second aspect of this could be one can provide something called anti-ramp bollards, or we can also use something called perimeter barriers. This is a very common thing what people use in port and harbors. Okay. So, one can provide anti-ramp bollards along the circumference of the ports. They will help reduce the stand-off distance, reduce the scaled distance, and they will help increasing the stand-off distance. They can be fixed, relocated and repaired. Okay. The bollards are adjustable structural systems which are rubber, neoprene pads or bearings which are provided along the circumference of the columns or the piles to avoid the blast effect. One can also use something called blast resistant facades. One can also use blast resistance glazing. Okay. The facades will receive the blast load first, and they will protect the building or protect the structure. But the main concern here is these facades upon failure will become projectiles and will be traveling at a very high speed, high velocity, which can cause further damage. So, that need to be taken care of in the design. One can also use something called laminated glass. You can also have something called blast rated curtain walls for the buildings. The fourth idea could be provide sacrificial cladding. These are non-structural elements which are designed to absorb blast energy. When they absorb, they get damaged, they fail during blast and they are replaced during repair. That is why it is called sacrificial cladding. Usually they are lightweight, but capable of absorbing blast loads. Usually they are applied and used in strategic structures. For example, definitely in maritime structures, but not on the entire structure, but on strategic areas on a structure. The last one could be easily, which we all know, could be an architectural consideration, where we can use something called internal compartmentalization. The whole structure can be divided into compartments, what we call as vertical and horizontal zoning, so that when the explosion happens in one compartment, the consequential effect does not travel to the adjacent ones. Usually this is generally practiced in offshore structures, offshore platforms, process platforms, LNG storage units, CNG storage units, and of course in port and harbors, which handles cargo of LNG terminals we call. So, let us summarize now friends, what are the important design considerations we have, which we have learned in this lecture. The design considerations as a summary, we can say that protective systems should be integrated with architectural and structural plans in the design stage. The second could be materials what is being used for construction should be tested for blast resistance. Systems must be maintained and periodically inspected properly. Okay. So, we have a design checklist which is generally done before we release the design for blast test and design. So, therefore, we must say that one must establish the design criteria, based on the threat level, then one should perform threat assessment, determine the charge of the mass, the standoff distance and the scaled distance, peak overpressure and consequence. Then one should estimate the blast loads correctly for various scenarios and consider the worst scenario for design. One can use equivalent single degree freedom system model to perform or incorporate the dynamic properties of the material and the system. One should ensure redundancy. So, the structure has alternate load paths. One should ensure strong connections, and one should verify the analysis and construction detailing before the design is released. Friends, so this set of lectures help you to understand thoroughly the design for fire, blast and explosion. We will take up examples in the next set of lectures and illustrate to you how to compute the fire rating for different kinds of problems. Thank you very much. Namaste.